Hello and welcome to the final Make It Move session. This is session number 7. This is where, as I've said 6 times before, you make it move, it being the robots. So this week is going to be kind of like a comprehensive review. Basically, I want to take this final session to point out what the most important aspects of what we learned are, because 6 sessions, each session being 40 to 50 minutes each, is a lot. So, it's important that we condense that down and so that you don't get really lost in everything. Now, obviously, the details are there if you need them. If you want to know how to write a specific function or how a specific thing works, then obviously that's an option. You could definitely go back and watch all of those recordings that we've had of previous sessions. But this week, I just want to point out which one of the things we've learned is the most important. So, tonight, we are only going to be doing 2 things. One is the comprehensive review, and 2, I'm going to kind of give you a longer assignment of things to explore. So this is going to be one of the shorter sessions. I would say probably 30 minutes. 25 to 30 minutes is a good estimate of how long this would be. So, yeah. So let's talk about some review first, and after that I'm going to give you some very important words. So before we begin, do you guys have any questions about what we're going to learn today, anything we've learned in the past? Okay, cool. Let's begin. So let's talk about what we learned in session number 1. So some of you guys weren't here for session number 1. Hopefully y'all looked at the recording, but these are the most important things that I want y'all to take away from it. First of all, why programming? Well, we program to let the robot run autonomously during the first 15 seconds of the match, and also to program the controls. So the link between what the driver's input and what the robot does, that bridge is the code that you create, that you program. So the types of files, we use command-based programming here at Team 2585 because we have a lot of mechanisms, and cramming all of those mechanisms, the code for all of that, into just one file or 1 or 2 files is very tedious. So we have a bunch of commands, a bunch of types of files here, as I show you for the 2024 code. So when you open it up, if you go to the link I sent in the code chat, if you click here, click on src main, you will be taken to the code, the bulk of what we use. And if you open up Java FRC robot, you're going to see all of the code files. So if you open them up, there's multiple types. There's obviously main and robot.java. These 2 files you do not touch. These are kind of more internal stuff that are handled by the compiler. Next up is robot.container.java. Unlike main and robot, this file handles, it's the backbone. It's the hub of where all the code comes together. This is where you put your autonomous commands, where you put your controls. Now you could obviously put those up into different files if it makes it more organized and easier to use. But this is where you put your subsystems and whatnot. This is where your robot comes together. Again, it's a robot container. Next up, we have constants.java. Constants.java just stores all the numbers. So stuff like port numbers, like maximum speed IDs for any Spark Maxes, any cans, maximum speed, how many teeth your swerve drive has, how many teeth the gear has, whether stuff's inverted booleans, PID values, just anything numerical. And then finally we have subsystems and commands. So commands are commands. When you run them, they do a certain thing. And subsystems are kind of the different parts, the code for different parts of the robot, the specifics, like what the motors are, how the subsystem would work during a when the code is run during a match. Finally, just an important function. This is probably the most important function regarding motors. .set spins the motor at a certain level. So, like .set, it's a number between -1, again, -1 to 1. 0 means stop. So what this does is just ends up setting the motor power to a certain level. So 1 being full power in one direction, and then -1 being full power in the other direction, the reverse direction. So that's session 1. Any questions before we move on? This is basically the most important things you need to know. You don't really need to know all the nitty-gritty, like the analysis stuff. That will come with a lot of practice. Spoiler alert for the next slides after this section. Any questions before we move on? Anything really. You could ask me what my favorite flavor of ice cream is, if you would like to. Hello? Alright. Moving on. By the way, my favorite ice cream flavor is vanilla, followed by cookies and cream, of course. Anyways, session number 2. This session was we talked more about hardware and software. So, this was just, I know, obviously, why do we need to learn software as a programmer? The reason why is because you want to be able to diagnose issues quicker. So, for example, if something's not working, you want to be able to interact with the hardware kind of on like the highest level. So, not like you don't have to know how to drill holes or how to you don't even know how to wire if you're a programmer. It's helpful to know, but it's helpful to know in general. You don't need to know you don't need to know the mechanical stuff. You just need to know at like the top level, the surface level, what I am working with here. And also, it's just a very nice thing to know. Expand your level of knowledge. So a robot, the stuff they're working with as a programmer breaks down to the following: motors, CAN, and encoders. Now, there's some that you could put cameras on. You could put cameras on your robot. You probably should put some sort of vision on your robot. Honestly, you will work with the radio and RPM for when you set the robot up, and you will work with the RoboRio when you set that up as well, when you image it for the beginning of a season. But most of the time, you're going to be working with motors, the CAN, which is this green-yellow wiring. This transmits code across the robot. It's like it's like a bus line. That's why it's called the CAN bus. And then finally, the encoders, which are inside of motors, or like you could attach them to a motor, and it measures the amount of rotation. Absolute versus relative encoders, speaking of, absolute encoders store the position of the encoder, the reading, even when the robot is turned off. When it's turned off, the reading will still stay the same. This is useful for stuff like swerve, so even if you turn the robot off and turn it back on, you don't have to calibrate it every single match. Relative encoders, they're usually more ubiquitous, and relative encoders, they get reset after you turn the robot off. Next up are SparkMax and Neos. So SparkMax, we have, this is the type of motor controller right here. This allows you to connect to any of the Neo products, so like the Neo 550, the Neo brushless motor, those types of motors, they connect to the SparkMax, and the SparkMax uses CAN. Next up are the Kraken X60s. This is the other type of hardware we use this season. Now, they're not here, but I think its most identical mechanical cousin is the Falcon 530 that's pictured on this wiring board. But yeah, Kraken X60s, once again, they're they sound like a lawnmower, very loud motors. Next up is the software that you use. Now, this is stuff that you absolutely need to know about. So we have WPI-Lib, which is the Visual Studio Code, the environment that we code in, like the extension. The environment is Visual Studio Code. The extension is the WPI-Lib suite, which gives us all the stuff we need to make an FRC program. Next up, we have FRC game tools. This is stuff like the radio imaging tool, the RoboRio imaging tool, stuff you need to set up all of the things. And this also includes the driver station, which is how you control the code, run it, which mode you have, all that type of stuff. Next up is Smart Dashboard. Smart Dashboard is it's the dashboard of like your robot. So you know how if you're in a car, the dashboard is like that shows you the speed, the revs of the engine, and all of that. That's what Smart Dashboard does, but for the robot. You can put whatever variable you want. It's very customizable. So we use Shuffleboard. Smart Dashboard it has a very outdated UI, so not everyone's going to be a fan of that, including myself. I'm not a fan of Dashboard. I use Shuffleboard for this season, and so did our drivers. We have the Rev Hardware client afterward. What this does is it allows you to connect and look at any SparkMax or related controller. And finally, we have Phoenix Tuner, which is the Rev Hardware client, but for the Kraken X60s, the Falcons, and all of that. So that's hardware and software. Again, this is something you need to know, because for the hardware, it's nice to be able to diagnose issues. It's nice to know what's going on, and it also helps you establish a better relationship with the manufacturers on your team. But for the software, you absolutely do have to know that, because if you're programming, you're probably going to be working with a lot of software. So are there any questions before we move on to session number 3? Okay. So session number 3 was about controls and commands. So first of all, we had the Xbox One. We had my whole spiel about Xbox One controllers, their button terminology. So what triggers are, what buttons like the bumpers are, joystick, X, Y, A, and B, what they're configured as, the D-pad, what that was. So this is the Xbox One controller, which is what we used for the 2024 season. Next up, I introduced you guys to configure button bindings and set default command. So configure button, these are just the two ways that you set the controls for something. So set default command is used for the drivetrain. And what it does is it continually checks, continually adjusts the speed of the drivetrain based off of the positions of these joysticks. And then configure button bindings does the same, except it allows you to kind of link one button's input to a command being run software side, and then that command ends up appearing on the robot. So set default command is used for buttons and subsystems, while configure button bindings is used for the joysticks. Next up, we just have what commands are. So this is how you call a command in configure button bindings. So this is just the general structure of it. The red means controller involved. The orange is the button involved. This is the condition. So on true versus while true. We never really use while true because that continually schedules the command over and over again. So there's no way to stop it. And I did explain what the difference between while true and on true is. So I recommend you guys look at session number 3's video for that. Next up is the parameters. Next up is the command that specifies the command to run. That's in cyan. And finally, we have the parameters of the command. So in this case, Amtrap PID, it wanted a set point. So we set that set point as source position. So this is just the overall anatomy of a command. Any questions before we move on? Okay. Session 4. This is the walkthrough for Tank Drive from scratch. So there isn't really much to review here because that entire week is very comprehensive. But we basically coded this thing right here. So has 4 motor controllers, 4 motors, a battery, wheels. This is how you move and get around. This is the most important part of FRC. All right. Session number 5. This was the PID control session. So we talked about why PID. Why do we have to implement code a PID for movement? And that's because you have to account for natural circumstances such as friction. So, like, for example, if you want to rotate something a certain distance, even if you get it down, if you get the calculations down correctly, it should work in theory, but in theory does not mean in practice. So usually if you say like turn the motor 720 degrees. It's not always going to go 720 degrees. And when you account for stuff like friction, the gears, they might slip a little bit, like the wheel slipping. Like these are all randomized things that you can't really control and you can't really predict. So you have to kind of adjust. You have to adapt to the circumstances. So PID stands for proportion, integral, derivative. And it's basically a continuous loop that sets the motor controller or whatever motors you're doing, whatever speed you're doing at, whatever you're trying to move, it sets that to a certain speed based off of what's called the error, and also the rate of which the error moves, which is derivative, and the sum of all of the errors, which is integral. Proportion is just how big the error is. And then next up we had tuning. For the last part of the session we talked about tuning. So these are the steps. Essentially it starts with KP, proportion, which does the brunt of the work. You turn it down until the oscillation is small, and then you raise Ki slightly, and then you smooth it out with KD. And we had the simulation thing where you were able to actually tune a PID and see how the ball moved with those settings. Any questions before we move on? And I'm going really quickly here, so if you have any questions, that's totally understandable. Totally fine. All right. And then 2 weeks ago, we talked about autonomous, with Swerve Drive specifically. So I introduced what odometry was. Odometry, it's built in for FRC. For other robotics competitions, you do have to kind of program that. Oh yes, looks like, no, it does not look like we have a question. Okay, so odometry is just the way for a robot to track its position using encoders in the motors. It does a bunch of math. The math is all done for you via library, so you just have to implement it. So this is what odometry is. It basically tracks the X position, the Y position, and the theta position. So this is orientation, so heading, as well as translational position. And theta is measured in radians. With the library we used last year, it was measured in radians. So as you can see, we had like math.pi and stuff. And we're gonna pray that 2025 does not introduce terrain, that Reefscape is completely flat field, because if it is terrain, that's gonna make our lives a lot harder getting an autonomous code working, because now we have to consider the third dimension, and also our wheels are gonna be 52 inches wide, or 52 inches long in diameter. So again, odometry, 3 parameters, X, Y, and theta. Theta being the direction of the robot, X and Y being its position. I also introduced sequential command group, which is a very nifty way of basically combining a bunch of commands, any amount of commands, into just one command. So this is the sequential command group, and it's essentially just a line-by-line code. After the first command runs, it runs the second one, third one, and so on and so forth. And then finally, I showed you guys, once again, how commands are scheduled. So the way commands are scheduled, once again, is if you have something like a PID command, it will not stop running unless you tell it to. It'll continuously move until something else is introduced, like if you force a control. Like, for example, if you have the pivot PID, you tilt it upward. If you move the PID, it will move. But until you control it to move, it will just continually update its position, or its speed of the motor. So that's why we had to code an auto pivot PID for the autonomous routine. Because if you just did pivot PID, it would keep on adjusting, because the thing is, the position the encoder reading is never the actual target we set it to. So it'll keep on adjusting itself forever unless we stop it. So we had to make an auto pivot PID to essentially stop the command after 2 seconds. That's down here at line number 59. So that's the command scheduling. It's a little bit weird at first. It feels a little bit unnatural, but I mean, once you learn how the commands are scheduled, then that's when it kind of starts to make more sense. Just kind of. Not fully though. Java and FRC code and WPILib can kind of be weird sometimes. So that was our session 2 weeks ago, and that is it for our review. That's like half of the meeting, not time wise, but in terms of content. Are there any questions about literally anything we've learned in the past 7 or so sessions? So if you weren't here for a certain session, you can definitely ask me about it. If you if you didn't understand it at the first time and you don't understand the second time, that's okay. You could totally ask me right now, and I'll be very happy to clarify. All right. So I just want to give you guys a message. So programming does not come easy to anyone. Now you might be thinking, oh, there's people out there definitely gifted. Even if you are quote unquote gifted and you're like even if you're him, like, or her, the one for programming, even if you are talented and gifted and like your parents are they're both known Java, C++, JavaScript, SQL, like assembly, all of the programming languages, you will still need hours and hours of practice to get good. Even the most talented programmers needed probably dozens, even if not hundreds of hours of practice in total, to master their language. So practice. Now, obviously, there's no robot to program right now. The robot is locked. It is currently being stored in a classroom at Belair High School. But when the school year starts, I will have plans to get us to program real robots, rather than just learn from these slides. These slides were meant to not be your only source of programming knowledge. It's meant to just be what programming is, what we do, like a sort of introduction to programming. For now, though, how might you practice, you might ask? Well, learn Java. If you know Java, then solve some, I cannot believe I'm recommending this, solve some LeetCode problems. Go on to LeetCode, Code Forces if you want to do that type of stuff. Do some competitions there, some contests on Code Forces. Solve a bunch of LeetCode problems. Because there's another half of programming, which is kind of problem solving, getting used to your language. And one of the best ways to know, to learn a language is to use it. Kind of like, I don't know, like it's like a muscle kind of. Like your biceps are not going to strengthen themselves. You kind of have to train it. You have to do stuff with it. Like, I don't know, another muscle group. Like I don't think your triceps are going to get strong by themselves either, or your legs. And I don't think your brain's gonna get stronger and other stuff either. There's the idea of being kind of rusty. And I know I'm rambling a lot, but you gotta practice with this type of stuff. You can't just learn it from a textbook. You have to interact with it and apply what you've learned. That's the other half of learning. And for coding, it's no exception. So either solve those LeetCode problems, do whatever practice you can, use some textbooks such as Head First Java, and they will give you problems, and you should implement those problems. Now, I recommend if you want to learn Java, I believe Replit gives you it's a free online compiler. Better yet is Eclipse. Those are both Java IDEs that you could use. And there are tons of guides on how to use these on the internet. Use those resources again. And that's another thing. Practice Googling stuff, because programming, a lot of programming, admittedly, and they're not lying when they say this. A lot of programming stuff is just Googling, knowing what to Google. If you have an issue, there's probably a solution online. So Google how to use these as well. Practice those Googling skills. All right. Finally, what's next? What additional software should we explore? Should we learn? So I did give you guys a list of the software that we already use, but there's a lot of other things that I would like to learn this year, and I'm sure Pranay, our programming captain, who's not here this year, would also like to learn. Get us to know. So the first one are path planners. The only software I have on here that is recommended, that I've seen recommended en masse, is Path Planner, stylized as this, created by Team 3015. And what Path Planner does is it allows you to make autonomous paths. and code them more efficiently. Rather than estimating the distance, the path planners will give you the code, or I'm assuming it'll give you the code, or it'll help you code, and you just all you have to do is just make a path. You have just to tap, 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 tap. It'll give you a curve. It'll generate a curve. You can adjust the anchors of the curve later. It's based off of like stuff like Bezier curves or something. Bezier curves are used a lot. Pretty cool stuff. So this is Path Planner. This is like the interface, and I just want you guys to go on to YouTube, see how people are using it, take a look at their website, what their features are. It's not like use it, it's just take a look at it and see how we could implement it. Or kind of try your best in seeing how we can implement it. And if you can't, then this is kind of just exposure as well. So I just want to expose you guys at the very least to what's out there, whether or not you could actually implement this stuff. Next up is Advantage Kit and Advantage Scope. What this does is it logs a bunch of data. It can do like simulations and stuff. It was created by a team like 6328. They are known worldwide as one of the software juggernauts. Not juggernaut necessarily, but as one of the software greats. And this is what they've created. They've created Advantage Kit and Advantage Scope. And this allows you to log your robot's data. It's very complicated. I've looked into it during this year's build season, and I figured it would take a very long time to implement. So maybe we could do this next year, maybe not. If you want something simpler, there's also the WPI-lib data logging software. It's not a specific program to download. Again, these are all programs you could download. This, I believe, isn't, but you could probably Google it as well. Again, Googling skills. So these are the two types of software that I want you guys to either just get exposed to or look into for the upcoming build season. Even if you're not a Belair student, like if your team doesn't use those softwares, try to see how you could use them and try implementing them next year, 2025. So your task. First of all, if you haven't already, create the tank drive code to get a feel of interacting with WPI-lib. It's a very comprehensive 21-step process. It'll definitely get you guys coding. But I would do this if you already know Java. Know Java first and then create the tank drive code. Next up, look into the softwares I have presented to you guys in these slides. So Path Planner, Advantage Kit, Advantage Scope, WPI-lib data logging. And then finally, enjoy the rest of your summer break. So again, those softwares I introduced you guys, it's not obligatory that you have to know how to use them. I just want to get you guys exposed to what's out there at the very least. And if you guys do figure stuff out, and you want to like share it to me, like information, key info about it, feel free to, and I'll definitely shout you out next opportunity I get. So, are there any questions about anything we have done in the past 7 weeks? Literally anything about Make It Move. Going once. Going twice. Going 3 times. Alright, if there are no more questions, enjoy the rest of your summer break. For HISD students, it's 3 weeks left, 3.5 weeks. You're welcome. But for the rest of you guys, if you're not in HISD, enjoy the rest of your summer break. If you're in HISD, enjoy what the little of summer break you have left. And I will see you guys, hopefully at Belair, this upcoming year. As again, I'm Dylan Wong. I'm an incoming senior. And I very much enjoyed these 7 sessions of teaching you guys how to make it move, it being the robot. Have a great rest of your week. Have a great rest of your summer. And goodbye.